Okay, so let us start again. So what we are looking at is the inverse equation, right? So we are trying to find the largest size eigenvalue of the matrix A minus rho I inverse for some non-zero constant rho, right? So that means we apply the power method which we already applied for the matrix A, right? For the matrix A minus rho I inverse. So we will have the same assumptions as we have in the other case, right? So let us assume that the eigenvalues are arranged in this non-increasing order, right? At the same time, similarly to the power method, here we assume that the eigenvector Z1, which is the eigenvector corresponding to the first eigenvalue 1 upon lambda 1 minus rho, is a component in the initial value, right? So if you look at the initial value, we see for the power method, we see that we take the initial value as alpha 1 z1, alpha 2 z2 plus alpha 3 z3, and so all the way up to alpha z, right? Alpha n zn, right? So here it's the same assumption, right? So this initial value as a part of z1 in it, right? So in that case, right, so then this sequence KR, right, will convert to 1 upon lambda 1 minus rho. And so then we can prove that the sequence KR converges to lambda 1 minus rho, which is the largest eigenvalue, right? So the proof is very similar to the proof we have in the power method. So I am not going to redo the proof again. As such, I will write this as a homework for you because it is very similar to the power method, but only thing is you change the matrix. Right? So that is the only difference here. Okay, so the proof is very similar to the power method which you apply for the matrix A. Right? So in that case, I leave it as an exercise. Right? So this proof you can do that, right? So let me write down that as a theorem here, right? So exercise, right? So if you choose x naught to be alpha 1 z1 plus alpha 2 z2 plus so on up to alpha n zn, right? Then you will have two things. One is kr converges to 1 upon absolute value of lambda 1 minus rho. The second one, right? So xr converges to some constant time c. Right? So as our question. Right? So this is what you have to prove, and this is very similar to what we did in the power method proof. Right? So there is no difference. Only thing is you just change the eigenvalue. Okay. So now let us see what is the application of this. Right? So we see we are saying that we are applying power method to the matrix A minus rho I inverse, right? And then we see that we can get the eigenvalue 1 upon lambda 1. This is lambda 1. 1 upon lambda 1 minus rho is something we can get. Right? So what is the use of this? Why we need to do this? So that following manipulation shows you what is the usage or importance of this inverse iteration. Okay. So let us say beta be the approximation of Kr, right? So limit of Kr is equal to beta, right? So you can get that from there, right? So that exact value. So then you know 1 upon lambda 1 minus b is basically an approximation for beta, right? So you know that it's not exactly equal. I say it is approximately equal. So from this you can solve for lambda, right? So I'm considering this as equal, right? So you can solve it for lambda. So what you get is lambda 1 is equal to rho plus 1 upon beta, or you can say approximately. And so you have lambda 1 is equal to rho plus beta. So this says, right, if you take rho as the first approximation for lambda 1, then this inverse iteration improves the rho. Right? So that is right. So suppose that rho is the value you obtained as the approximation for the eigenvalue lambda 1 by applying the power method, right? So when we, if you look at the example we did in the last class or class before that, you know 9.125 is the eigenvalue, right? But what we get as an approximation is 9.12444, something like that, right? So that is slightly away from the original exact value, right? 9.125 is the correct value, but what we get in numerical computation is 9.1244, right? So then there is a difference. 0.0006 is the difference. So that difference can be improved by using the inverse iteration, right? So if you take beta as the value you obtained in the inverse iteration, 1 upon beta plus the previously computed value is an improved approximation for the lambda 1, right? So in the examples where you have a big error in computation, right? So because of some certain round offs and other things, you can always apply the inverse iteration and improve the error, right? So that means you can improve the approximation by reducing the error. So this inverse iteration is basically working as a error reduction mechanism in eigenvalue computation. So now let us see how we can apply this inverse iteration. Right? So that turned out to be another type of problem because of the fact that you have inverse of a matrix in the computation. Right? So how to implement the inverse iteration? Computations. So this is the inverse equation you have. Right, so this is the inverse equation you have, right? But unfortunately, you have to handle an inverse matrix, right? Right, so we don't want to use this because in numerical computation, finding an inverse matrix is a very painful and difficult computation, right? Especially because of this application, you know that you choose rho as the approximation to lambda 1. So already rho and lambda 1 are very close, right? Like in the example I said, 9.125 and 9.1244. So they are very close. So already lambda 1 and rho are equal to each other, almost equal to each other. So in that case, it is sometimes some computational softwares may not be able to compute the inverse of the matrix because it is almost singular, right? A minus rho I turned out to be almost singular. So inverse is very difficult to compute. So we always want to avoid this inverse computation. So how we can do that? Let us do a slight manipulation in order to avoid this computation. Okay, so in order to do this, let us rename this part, right? The part with the inverse matrix, let us rename it as, right, ZR plus 1, right? So let us rename it as ZR plus 1, right? Then the inverse iteration will look like this. Right, so obviously ZR plus 1 is the term A minus rho I inverse KR. So in the equation, you know KR is the largest size component in this vector, right? So that means it should be the largest size component in ZR plus 1. So you reduce or you rewrite this inverse equation in this form, right? So now the point is you want to find what is ZR plus 1. How do you find ZR plus 1? So let us right? So first you want to compute ZR plus 1 at this step, right? So that means you want to solve this system, right? So if you want to solve this system, you rewrite the system like this, right? XR plus 1, sorry, XR is equal to, you move this inverse to this side, so ZR plus 1, right? So now you know XR is given, this is given. So this looks like a matrix system. AX is equal to B, very similar to the system you studied at the first chapter, right? It is a matrix system of a system of linear equation. You want to find this vector ZR plus 1, right, which is equal to X. A times ZR plus 1 is equal to XR, right? Right, so this is very likely of solving the system AX equal to B. So you go back to the chapter 1 and look for LU factorization, right? So you know, in chapter 1 you studied about factorization, LU factorization. PA is equal to LU factorization, right? P permutation matrix right? L unit lower triangular, U upper triangular. Okay, so this. Okay, so let us continue. So this is the material we covered on the first chapter, that is factorizing a matrix A as PA is equal to LU. Here your matrix is A minus rho I. So suppose that you factorize that in the form PA is equal to LU, right? So then you know that this. So like the way we studied in the previous case, right, in first chapter, right? So what we do is we write the matrix A minus rho I as P A minus rho I is equal to LU form. So A minus rho I is equal to P inverse LU, right? So you substitute here. So you get P inverse LU times R plus ZR plus 1 is equal to XR, right? So that means LU times ZR plus 1 is equal to PXR, right? So you know how to solve this, right? So you set this thing as YR plus 1. So you ended up with a lower triangular system. L times YR plus 1 is equal to PXR. Here you know everything. XR is given. PXR is the previous step. Given P is known. L is known. So you can compute YR plus 1. Once you compute YR plus 1, then you know U times ZR plus 1 is equal to YR plus 1. So U is an upper triangular matrix. You do back substitution and solve it. So then you get ZR plus 1. Once you get ZR plus 1, you know you can go back to the iteration and compute the next step. Right? So this is a lengthy process, but this is the easiest way or the less expensive way in terms of computational time, right? When we do a computerized programming to do the computation, if you follow this procedure, this will save the computational time rather than going for an inverse of a matrix, right? So when you go for inverse of the matrix computation, sometimes the matrix, inverting the matrix may not be possible, but PA is equal to LU factorization will always work irrespective of the matrix. So in that case, you can always simplify this and solve the system, right? So now the point is, what is the cheapest idea to solve the system, right? So let us see first an example and we will see how we can simplify the system, right? So by doing an example, we can see how we can apply this inverse iteration, right? So the procedure is simple, right? So you always apply the power method for the inverse of the matrix, but because of this inverse matrix, you change it back to PA is equal to LU factorization. Right? So let me give you an example. Right, so let us suppose you consider a matrix, right? So A be a matrix of this form, of this with this component, right? So A is equal to this, right? So you can always find A minus rho I for this given row, right? So now it is given to you that rho is this, so you don't need to compute the power method first and get the row. They gave you the row, so all you need to do is you need to find this A minus rho I. This matrix is something you have to find. So you know that you will get this 0, minus 1, 0, 1, minus 3 over 2, minus 3 over minus 6 over 2, so it's minus 3, 0, 1, minus 3, minus 3. Okay, so this is your A minus rho I, right? So after getting A minus rho I, what you have to do is you have to go back to chapter 1. You need to get PA is equal to LU4, right? So you have to do Gaussian elimination with pivoting, right? So I will do that. So first step, you have 0 on the first term, first diagonal term, so you have to avoid that, right? So now I can write down the notation and you all know the meaning of that, right? So P12 times A minus rho I, right? So if you find P12, that is permutation matrix, interchange rho 1 and 2, right? So that is going to give you 1 minus 3, 0, 0 minus 1, 0, 1 minus 3, minus 3. Right. Next step is you have to evaluate, you have to eliminate, right? You have to eliminate this 1. So your M1 is 0, 0, 1. Remember, it's all chapter 1, right? So L1, M1 times P12 times A minus rho I. It is elimination part, right? So first 2 rows don't change because your M1 0, 0, 1. So only the last row is what it's going to be evaluated, right? So 0 minus 1, 0, 0, 0 minus 3. So fortunately for you, this is already an upper triangular matrix. Okay, so this is already upper triangular matrix. So you don't need to worry about one more step. This is already upper triangular. So your L is L1 of minus M1. You all know that, right? So you move this L to the other side to get PA is equal to LU. So L is minus L1 of minus M1, inverse of the matrix. So that you can write it down because you know M. So it's going to be 1, 0, 1, 0, 1, 0, 0, 0, 1. Right? And then you can find P. That is only P12. And P is equal to P12. So it's going to be 0, 1, 0, 1, 0, 0, 0, 0, 1. Right, so after finding A minus rho I, right, so you can find PA is equal to LU factorization and you can find L, P and U. So here you already know U, you can find L and you can find P. This is all what we learn in chapter 1, right? So now you know it is just about solving the system, right? So once you do that, you can always try to solve the system. Okay, so now let me give you a hint, right? So this you can always use, right? Right, so we always use the initial value x naught as P inverse L times E, right? So we can always use P inverse L times E, right? So in that case, right? So if you choose P inverse L times E, right? Then always you will get y1 is equal to e, right? So you can check this out, right? So if you put x naught is equal to P inverse L times E, right? Then you can easily see that y1 is equal to E, right? So by using this, right? So you know this is the formula. And so you have L times yr plus 1 is equal to Px r, right? So if you put x naught is this, you know y1 is equal to P inverse Le. So eventually y1 is equal to this, right? So from this, if you put this x naught and this together, give you this. Right? So you can easily verify that. So once you know that, then you can always do the computation, right? So computation part is just as we do in the power method. So there is no trick there. The only thing is you can use this, right? And so you know this is what we have to solve, right? So given x naught, which is P inverse Le, right? So if you are given this x naught, then what you do is you solve these two, right? L by r plus 1 is equal to P x r, right? And then u z r plus 1 is equal to y r plus 1. So these are the two steps you have to choose, right? So once you do this, then you do this, and then you do this, right? So xr plus 1 is equal to 1 upon kr into zr plus 1. Right? So you have to do 3 equations. You have to solve 3 equations at each step, right? X naught you can always choose like this, so you can avoid doing some computation, right? If you choose x naught like this, always your y1 will turn out to be this, right? So that is the next step. You find y1. So you can always make a table like this, right? So x naught you already choose, right? So I don't rewrite it again, right? If you choose x naught, you can say you have to find y1, right? So in this order you have to do. Right? First you solve this, second you solve this, third you solve this, and then you go back to here again. Right? So this is how the iteration works. Right? So y1 turned out to be E. So that is 1, 1, 1. Once you find y1, right, then you have to find z1, right? So z1 is you have to solve this equation, right? So which you all know how to do it. Right, so I will do the first step only, and then rest I will leave it as an exercise. And so then you know you have this. U is 1, 0, 0, minus 3, minus 1, 0, 0, 0, minus 3, right? And then z1, so let me name this z1, right, is equal to y1, that is 1, 1, 1. Okay, so from this you know you get, okay, so let me clearly indicate you. Right, so the third component of Z3 is 1/3, right, minus 1/3. And the second component is minus 1. And then the first component is 1 plus Z3 is 4. So move that to the other side, plus 3 times 1, 2, minus 2. Okay, Z2, Z1 is this. Once you find Z1, you know you can get K naught, right? K naught, power method. the component with the largest modulus. So among these numbers, you have -2, -1, -1/3, right? So in these numbers, you know -2 is the largest sized number, right? Among these numbers, -2, -1, and -1/3, -2 is the largest sized number. So your K naught is -2. Once you know K naught, then you can find X2. Sorry, X1. And X1. X1 is 1 upon K naught times Z1. So you divide everything by -2. So you get 1, 1/2, 1/6. Right? So this completes the first step. Then you get Y2. And so Y2, you know you have to solve this. L times L is 1, 0, 1, 0, 1, 1, 0, 0, 1 times Y2, right? So Y1, 2, Y2, 2, and Y3, 2 is equal to P times XR, right? So P is P23 times this, right? P23 times this. So P23 times this is this. So you have to interchange the first and second rows. So you get 1/2, 1, 1/6. Right? So 1/2, 1, 1/6. Right? So then clearly you can find Y2. Right? So the first component is this 1/2. From this you get 1. From this you get 1/6 minus 1 minus 1/2. And so minus 3, 2 plus 1, 6. So minus 9, 6 plus 1. So it should be minus 8, 6. Okay, so this is your Y2. And then you can continue. You get Z2. And then you keep on continuing like this. Right? So if you continue like this, you will end up finding the next iterations as the components of inverse iterations, right? And then you can keep on computing K0, K1, K2, K3 and so on, and then you can get an approximation for 1 upon lambda 1 minus rho. Right? So that should be the approximation basically for the error in the 1 upon error in the computation. So this is how you do the inverse iteration. So these are all the material we are supposed to cover in the linear algebra part of this course, right? So and then the next section is for another 10 to 15 hours. It is for numerical differential equation that will be taught by Professor Vigneswaran, right? So he will, your head of the department will contact him and arrange a timetable with him. So as of now, what I am going to do is I am going to stop my part of lectures from today, right? And then I will talk to your head and he will let you know about the other part. So still I don't know what the department and the dean are deciding about calling you back. So ICA 1, right? As of now, I will not tell you anything about when to conduct the ICA and anything. So once the department and the dean decided to fix your exam timetable and all the things, this exam is going to be at the end of the second semester. So you don't have final exam for this course in the first semester. So you will have it in the second semester. So once those days or dates are fixed, then I will contact all of you through your head of the department and try to arrange ICA 1, and then maybe once you come back, we can do a revision class or something also if we have time and everything. So as of now, we will stop this linear algebra sections of this course 419, and then your head will communicate with you about the other part of the courses, right? So I will do some kind of brush up course, and I will talk about ICA when the faculty decided to call you back to the university, right? So that's all I have to say. And if you have any question, feel free to contact me directly or through your head, right? So the other part of the course, the head will inform you about the time and everything.